Okay. So first, let's discuss what are insulators, what are conductors, and what are semiconductors. So we have a nucleus, that's a center of an atom, and we have electrons. And here we have conductance band. It starts from here to here. So that would be conductance band. Okay, if that's an isolator, distance between electrons and conductance band is large. So that would be an isolator, so few electrons. Semiconductor is like this, but it has more electrons that are closer to conductance band. So conductance band starts here, and the outer electron is close to conductance band. And in case of isolator, conductance band is far from the outer electrons. And in case of conductor, that's nucleus, and it has a lot of electrons, and they are in conductance band. So conductance band starts here, and electron is in conductance band. Okay, so why are they called bands? Can you disable sound, please? Okay, so if you have, say, two stands and you have rope, and you start, and that's rubber rope, and you start like in this position. So you grab it and you let it go, then it will go up and down in stationary wave. So like this, it will go from this state to this state, like infinitely. But if you have, say, two stands again, and you initiate rope in this state, so you pull down and you pull up, then you release it, then it will go up and down in stationary wave like this. So periods of this wave is like 1, half, 1/3, 1/4, and so on. So periods of these waves are quantized, and these are bands. So you can think of this like this is like a visual representation of why positions of electrons are quantized. By the way, after I finish, I will ask you to say what I've just said. So you will have to explain to me what I'm explaining right now to you. Okay, so you may heard of guitar bands. So then you drag, how do you call it? Struna. String, yeah. So then you grab string and you release it. Then stationary wave is generated, and the stationary wave is quantized. So that's why quantum physics, the wave is quantized, and positions of electrons are quantized. So if you want to make a semiconductor a conductor, you need to excite outer electrons. You can do it in several ways. Like you can heat the material. So you give energy to electrons and they jump to outer band. Or you can excite them using photons. So if a photon is gets to the electron, it's like piece of wave is added to stationary wave, and it kind of visual representation. So it kind of elongates the radius, and it gets bigger, and it gets to the conductance band. So that's the second way how you can make a semiconductor conduct. You can heat it, or you can emit light on it. Okay, so isolator has large distance from outer electron to conductance band. Semiconductor has small distance from outer electrons to conductance band, and conductor has electrons in conductance band. You will have to explain me that later. Okay, now let's clean it up and see what current is. I hope you understand. You understand me more or less, right?
So.
Okay, nice. So we have a wire that we'll think of as a tube, and this tube has like balls inside. As you apply voltage, so what does it mean to apply voltage? You push electrons like in some direction. So as you push with this electron in this direction, it makes other electrons move. So all of them simultaneously move. So for example, if you grab a motor or generator and you and you rotate it and you have some resistor on outer coils, then you feel the resistance. What you're actually doing is that you're accelerating electrons inside of the wire. So the power source is a device that forces electrons in some direction. And by the way, these electrons are not connected with some kind of springs. They are rigidly connected. At least you can think of this like this way. Electrons, as you start moving this electron, recording. As you start moving this electron in this direction, this electron starts moving almost instantaneously. So information propagation speed is defined by the speed of light and distance from this point to this point along the wire. Okay, so now we have that wire and the power source and semiconductor material. So you can make this material conduct in several ways. First, you excite electrons to outer layer to conductance band, and as it has electrons in conductance band, that allows electrons to jump from one atom with electrons in conductance band to another. So if you have electrons in conductance band here and here, they can jump from one to another. If you don't have electrons in conductance band, they cannot jump. So you hit the material, electrons jump to conductance band, and it starts conducting. The other way, you emit light on it, and electrons jump to conductance band, it starts conducting. The other way is you make this semiconductor narrow, and you have quantum tunneling. So we need to know all ways in which we can make semiconductor conduct, because we will use that semiconductor as a switch. So the switch conducts electricity or it does not conduct electricity based on some reasons. Okay, if that semiconductor is let's say not too narrow for quantum tunneling and not too wide to be a resistor, then if like say metal like copper or aluminum has electrons on conductance band, these electrons have some kind of mobility, so they can like move away from the nucleus to some distance, and if that distance is not too wide, then they can go through semiconductor if semiconductor is in kind of resistant state. Okay, so there are two other ways to make semiconductor conduct: is to dope it with p-doping or p-type doping or n-type doping. So we have silicon atoms, and each silicon atom has 4 valent electrons on outer layers. We will draw 2D representation of a crystal, but actually silicon crystal is certainly 3D and it's not connected the way we draw it on the board. We just making life simpler. Okay, and by default silicon has all electrons on not in conductance band, so it's an isolator by default. But if we replace this silicon atom, for example, with phosphorus, then phosphorus has more electrons than it is needed to make a crystal structure. So it has like fifth electrons. So silicon has 4 valent electrons and phosphorus has 5 valent electrons. So it has additional electron, and as you apply voltage, say in this direction, so if you apply voltage in this direction, then you tell electron to go this way. So voltage this way, electron goes this way, and that electron jumps from here to here, then jumps this way and this way. Adding just a tiny bit of phosphorus make semiconductor conduct. The other way is to replace phosphorus with boron, and that gets a little bit more complicated, as boron doesn't have has 3 valent electrons on outer layer. So you have a hole here. So you can think of this missing link as a hole. So as you apply voltage in this direction, the hole, let's draw it on the other way, on the other side. The hole, which is here, starts jumping around. So it jumps here. So what happens is you have now a link here and hole here. Then it jumps this way. So you have a link here and hole here, and so on. So hole jumps in this direction. That actually means that all other electrons move in the opposite direction. So we had we can heat material to make it conduct. We can emit light on it to make it conduct. We can add p-type doping, which is phosphorus, for example, which has excessive electrons that make it conduct. Or we can add sorry, that was n-type doping. Or we can add p-type doping like boron, which doesn't have enough electrons, which has less electrons, which has less valent electrons than, for example, silicon. So we have holes, and that way we have conductance through holes. Okay, so this is like the complete set of making a semiconductor conduct. Okay, so now let's see how we can make an electronic switch. Oh no! First let's see how we can make a diode, using several types of dopings. Okay, so we have n-type doping, which is like phosphorus rich, and we have p-type doping, which is boron rich. So what happens is we have some holes here. Sorry, we have holes here on this side, and we have electrons here. And these electrons, they need a job, so they are jobless. And these holes are like vacant positions. So jobless electrons are searching for vacant positions, so they occupy these holes, and this region becomes so-called depletion region. Depletion region. Okay, so atoms are neutral by default, so their charge is neutral, and as electrons move from this place to this place, this area becomes positively charged. Once again, so the nucleus is positively charged, electrons are negatively charged. Negatively charged electrons move to holes, they occupy holes, and this area becomes positively charged. Once again, okay, so nucleus are positively charged and electrons are negatively charged. So we have neutral charge here. So as negative charge moves to this side, then positive charge stays here. So negative moves to this side and positive stays here. So this area becomes positively charged, and electrons move here. So there are more electrons here. Electrons are negatively charged. So we have negative charge here. So we have a field of charge along the path in which we want to conduct electricity. So we have, for example, lamp here, and we have like power source. So this diode can conduct electricity in only one direction, and in that direction it's like it looks like this. So we have like positive and negative. Let's redraw it. We have like, let's redraw it again. The graph would look like this, for example. So this is like neutral, and for example, we push electrons in this direction. So they're like fluid. So as soon as they occupy this space, they tend to overflow in this direction, and we have the current. So that voltage is approximately 0.7 volts, 0.7 volts. So in direction in which diode can conduct, we still need to apply approximately 0.7 volts to make it conduct. But in other direction it doesn't conduct. Okay, that's the basic idea on how diode works. The girl that was supposed to be here, she is modeling the diode in Visual TCAD, is modeling some special type of a diode. It's called point contact diode. So it has a large P area, P, and then wire, which is of N type, is pushed hard against this N type region, and so the smoothness of this region is very low. So it's not, there are two ways to dope the P region. So if you have like P region and we like add some chemicals here, then we heat it, and for example phosphorus from this region enters this region, then there's no like straight light of doped region, so it's like smooth. And in that case, in point contact, it's rigid, so it's no smoothness. Okay, now let's look at field effect transistors. There's one else way to make a semiconductor conduct, which I haven't told you before, is to apply electric field to it. So for example, you have like a lightly p-doped wafer, and you apply voltages between here and here. This will be like positive voltage, and this is like negative voltage. Positive voltage will attract negative charges here, and negative voltage will attract positive charges, so holes here. And if that is long enough, then if you apply voltage, if you like connect metal to here and connect metal to here, it will start conducting. Okay, so now let's build a transistor using field effect. So we have substrate, we have N regions. That's what you're actually modeling in COMSOL. We have metal contact to base. This is slightly p-doped region, and we have isolated gate. So we apply positive voltage to the gate, and we have negative charges here, and so we build the channel. So this transistor becomes a conductor. So we have, for example, like voltage source here, and we have lamp here, and as we apply voltage to the gate, it starts conducting. If we do not apply voltage to the gate, then it will start. So let's slowly increase voltage between gate and substrate. The graph will look like this. So this is the threshold voltage. So if we apply small voltage, then there will be no current, because we have depleted regions here and here. Okay, so for example, we need this transistor to perform operations like conduct, don't conduct, conduct, don't conduct. Are you listening? Yeah. So we need. You will have to tell me that after we record the video. Mm-hmm. So it conducts, it stops conducting. It conducts and stops conducting. So we apply to make it stop conducting. We can just unlink. We can unlink voltage source from gate. But what will happen? Due to leakage, the transistor is like a capacitor, so it has like, so it works like this. So if you charge it, it has positive charge here and negative charge here, and capacitor will eventually lose its charge. So due to leakage, current will leak and it will discharge over time. But that's not what we want to happen in processors. We need the capacitor to discharge fast. Okay, so one way to discharge the capacitor is to link substrate to gate. So we can simply link them together. What will happen in that case? The discharge graph will look like this. So that will be time, and that will be charge. And charge will drop like this, so not to zero. From this voltage, so this is like a voltage at which you stop having the channel. it will stop conducting and it will switch off. But that wouldn't happen fast enough. We want it faster. To make it, we will not just connect them. We will apply voltage in the opposite direction. So we will make this voltage negative and this voltage positive. So what will happen is, so the same graph with time. So the charge will drop like this, and that will be like negative. Much faster. You see the difference. But after that we will have to charge it, and we need to spend energy on charging. That energy is current, so it will have to draw the current. The less current transistor draws, the better. So we can change this discharge voltage, like for example to this, and that will happen a little bit slower, but we will have to recharge it a little less, much less. We will spend much less energy on that. Okay, so that was the part with the single transistor. Now we need to perform mathematical operations on transistor using transistors. So we will have memory cell from which we send data to our mathematical block. That memory cell will look like this. You won't find this on YouTube or anywhere because that was invented by me. So we have two output pins on each memory cell and two input pins. Two input pins will have feed voltage from different sources. So that will be one source, and that goes somewhere, and that will be another source that goes somewhere. So this will be like positive terminal, this will be negative terminal, and this could be negative or positive. So we encode 0 as plus 1 volt and minus 1 volt. So that will be terminal A and terminal B. So that's terminal A and that's terminal B. So if we have like plus 1 volt on terminal A and minus 1 volt on terminal B, then it's 0. 1 is encoded the opposite way. So it's minus 1 volt and plus 1 volt. So that will be, so 1 will be minus here and plus here. So that memory cell will look like this. That memory cell will have two states. These are inputs, these are outputs. State 1 is like this. So they are just minus connected to minus and plus connected to plus. And state 2 is like this. Like this and this. So they are reversed. Okay. Now as we have memory cells, let's feed data from memory cells to our logic unit. Thank you. Our logic unit will perform additions of two single bit numbers. So we have number A and number B. It could be 0, 0, 0, 1, 1, 0, 1, 0, and 1, 1. So as we add two numbers, we have 2 bits on output. That will be like result 1 and result 2. Result 1 will be XOR of A and B. So it will be 0, 1, 1, 0. And result 2 will be AND of A and B. So that will be 0, 0, 0, 1. Okay, so 0 plus 0 is zeros. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 1, 0. That is 0, that is 1, that is 1, that is 2 in decimal, and that's binary. Kind of simple. Okay, so we have two memory cells, A and B. So that will be memory cell A, and that will be memory cell B. First, let's start with AND operation. So you see this is like 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. That's AND operation. That's AND. And that's XOR. So if they are different than 1, if they are equal, that's 0. That's XOR. Okay, so let's start with AND operation. We have outputs and outputs. That's B. That will be outputs. Okay, so we will have substrate we will have N region, another N region, and another N region. Our output will be lamp, so that's substrate. It's lightly doped P substrate. So output goes to the lamp, and input goes to voltage source, and that is connected. We will have A and B. So so that will be output A, and that will be output not A. That will be output B, and that will be output not B. So if we are listening.
Yes.
Come on, record. Hands off. Okay. So if we apply positive voltage on both of them, then we will have negative charges here, and both of them will conduct. So that all becomes a conductor. That will happen only in the case if both voltages are positive. If that thing is a conductor, then it conducts and lamp lights. If any of these voltages are negative, let's see what happens. Okay, so we have N region, and N region. Okay, if that is negative, and that is negative, that actually means negative between these points and a substrate. I haven't drawn the entire schematics, I will enlarge it. So we will have two power sources that are connected to substrate. One will be connected with negative terminal here, and another will be connected with positive terminal here. We'll also have negative terminal here, and another terminal is positive. So if we apply both to negative, that actually means that A and B are connected. They are both negative and they are connected, and they both are connected to this power source. So we have negative, that means we will force electrons. So we have negative electrons here from the previous state, and we force them out of here. So that's the forced discharge. So we had a capacitor, and they forced the capacitor to discharge, and that happens in this position and in this position. So if we have like 0 and 0, then we force capacitors to discharge. Okay, if we have if one is plus and another is minus. Okay, that means that they are not connected, and plus is connected here, and minus is connected to here. Okay, that forces discharge of this capacitor, and that charges this capacitor. But anyway, the current cannot go from here to here, so we have a channel here, so that one becomes a conductor. But we don't have channel from this point to this point, so the lamp doesn't shine. And in the opposite direction, it will happen the same. Okay, now let's see how XOR works. That's a little bit more complicated. That was easy. We are almost finished. Not almost. Okay, so XOR. So we will have 5 N regions. That will be N region, another N region, another N region, and another N region, and the last one. Okay. That is slightly doped P region. So I hope you remember that XOR looks like this. So that's A, that's B, this is B, and this is A. Sorry, this is A and this is B. That's not the end. Okay, so another way of showing the same schematics is using all the N-types. So for our substrate, we will use all the N-type transistors because they occupy less space and because it's easier to make them. Quite a few reasons for that. Okay, another way to draw the scheme is like this. So this is like input, and we will use only N-types, so only normally non-conducting switches. Okay, that will be A, and that will be not A. that will be B, and that will be not B. Okay, so you can first, to simplify it, we can draw it first in a bit simplified way. We will draw two transistors. So that transistor will be first row, and that transistor will be second row. This is N, N, and N. So we apply here A, we apply not A, and oh, that should be not B, and that should be B. Okay, so we apply not B and B. Okay, so now we connect these two together. So we kind of make it on the surface only. So we enlarge it. So that will be B and not A. Okay, so we enlarge it. That will be N and N. So we apply B and not B. Not B. Okay. So these are the same. That substrate is connected to two power sources. Like the entire vapor will be connected all the time to two power sources. So that will be negative terminal, and here will be another power source with positive terminal here and negative terminal here. Okay, and now we will redraw this table. So let's draw now with positive and negative voltages. So if both voltages are negative, we shall not have a connection. If negative and positive, we shall have a connection. If positive and negative, we shall have a connection. And if positive and positive, we shall not have a connection. Between what and what? So this is so that will be the lamp. That will be power source, and that is connected to here and here. Okay, so let's see if both are negative. So that's A and that's B. Okay, so A is negative, so we have negative voltage here, and that is supposed to be A, right? No. One second. So that's A, B, A not, so B not, B not, B. So that will be, so that's A. That's A and not non-inverted A. So that's A, standard A. Oh no, sorry, that's inverted A. That's not inversion. So we have minus to this point. Okay, and that's inverted A, so that's plus. So plus goes here. Okay, now B is minus, and that B is plus. Okay, so pluses are connected, and minuses are connected. Minuses are connected to this one, and pluses are connected to this one. Okay, so we have positive voltages here, so we have electrons here, and we have a channel. We have positive voltages here, so we have electrons here, and we have a channel. But you see, neither from here nor from here we can reach this point. So lamp would not shine. Get it? Okay. I'll explain you once again as we get closer to the topic. Now we need to get the general idea. Okay, that was the first case. So we had no connection. So now we shall look at second case. So A is positive. So we have positive here, and node B is negative. So we will have negative here. Now B is negative, so we will have negative here, and node B is positive, so we will have positive here. So negative is connected to negative, positive is connected to positive, both positives are connected to positive, and both negatives are connected to negative. So we have positive and positive. That actually means that we have electrons here and here, and we have a channel in both cases, and we have both of them negatives, both of these negatives, so we don't have a channel, and these capacitors are forcibly discharged. So these are forcibly charged and these are discharged, and we have a channel, like this entire thing is a channel, and we have a conductance between this point, so the current can flow this way, so lamp shines. Same will happen in this case, but in this case this part will conduct, and in case both of them, none of them will conduct, so it works. So now let's draw the entire schematics for now we have XOR and AND. That's enough for us to make a ALU that can add two single bit numbers. But substrate is, that was 1D representation, but substrate is a 2D structure. So it will have, we'll use some specific way of arranging N-type dopings. That will be grid array. So we will have like a grid, okay, and we will have N doping here, N doping here, N doping here, 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 and here. So we can't have, we need at least like one square between. Are you recording and listening, right? Okay, so we have at least one square between each N doping, because fields that are generated between this, and can you please be more silent? So fields that are generated between these N regions should not overlap. They must be independent. Okay, so first let's see how AND is done. For example, we have like this N region and this N region. So this will be connected to lamp, and this will be connected to power source. And we will have A here and B here. So if we apply positive voltage on A and positive voltage to B, then that entire part becomes a conductor, and light is emitted. So if both of them are positive, then the lamp shines. If either of them is negative or both of them is negative, lamp will not shine. Now let's see XOR. So we will use, let's clean this up. Let's place XOR in this part. So that will be connected to lamp, that will be connected to plus, and that will be connected to plus. Okay, so we have A and not B, and B and not A. So if, let's say, A is positive and B is negative. If A is positive, then let's see this one. If A is positive, then we have plus here, and if B is negative, we have plus here, because it's not B. So we have conductance from this point to this point. In other way is, if A is negative and B is positive, then we have A is negative, so this square becomes positive, and this one is positive because B is positive. In that case, we have conductance from this point to this point. So if A and B are different, then we have conductance either through this path or through this path. In any other case, we don't have conductance, so the second lamp doesn't shine. Okay, now we have, you might have noticed that this NAN region is similar to AN, BN. So we can add B here, and we can add lamp here. So let's draw like lamp is here, and lamp will be here, and that's another way. So if, for example, A is positive and B is positive, then this becomes a conductor and this becomes a conductor, and we have a path. Okay, if either of them, A or B, is negative, then we don't have a conductance, and this lamp doesn't shine. So that's AND, that's XOR, and this is the mask we will have to finally build. Okay, so as soon as we get this mask, that will take forever, we will have to build physically our chip. We will do it this way. So we have silicon wafer, a lightly doped p-type silicon wafer, and we need to make this grid of n dopings. So here, 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 and here, here, here. And that's a cut like here, for example. So we will have, and so we need to have like n dopings here. So what we will do is first we will spin coat this n-type substrate with photoresist, and we will apply UV light through mask, and mask will look like this. So this is a mask. So light will shine like this, and oh, sorry, not like this. So line like this. Oh, it actually doesn't matter. Okay, so light will shine like this, and it will solidify parts of photoresist here. So it will solidify here, photoresist here and here. Okay, next we will wash off photoresist and apply some chemicals here, here and here. And we will heat those semiconductor, and those chemicals will dope this region with n-type doping, for example, boron. This way we will get n-type dopants. Okay, next we will remove that photoresist, and we will have another mask using which we will build, we will solidify photoresist in this region and this region, sorry, and this region. Okay, and we will grow metal here. So we will have metal contacts here, here, and here. This way we will get connected to n-type semiconductor. Okay, next, as we have metal contacts here and here, we will grow insulator here. Okay, same step with photoresist, but in that case we will heat up the semiconductor and apply some water vapor within some reasonable amount of time, and we will grow silicon oxide here. So here and here we'll grow silicon oxide, thin layer. That's possible, that's not too complicated. And we will grow later metal contacts here and here. So that will be our final product, but we will also need to connect these metal pieces to some circuitry that will connect lamps and all other stuff. We will order from JLC PCB the circuit cell. We will design it in easy EDA. Then we will apply solder paste to the points of that circuit. We will reverse it and place on top, heat it, and solder will connect all the pieces together. And that will be our final product. Done. Okay, got the
So?
yeah.